All right, welcome to lesson 2 of unit 7. Today we're going to talk a little bit more about Riemann sums, and I'm going to introduce something called the definite integral. Now, so in the previous lesson, we worked mainly with preset intervals. We started with intervals of length, I think, like 2 each time, or 3, and then we looked at intervals of a half each time. But then in our last example, we saw that that's not always the case. So I've got this curve here, and this is going to be f. Okay. To estimate the area bounded by the graph of f of x and the x-axis between a and b, we can partition the area into some amount of subintervals of various widths. So let's do that. And I'm just going to partition this in the various different widths. So here, maybe a smaller one, maybe this one will be bigger, medium, another small one, maybe a medium, a little bit bigger, etc. I'm going to construct. So for this is in subintervals, right? Okay, but let's talk about how many of these different things. I got 1, 2, 3, 4, 5, 6, 7, 8. I got 9 subintervals here, and I had to pick points 1, 2, 3, 4, 5, 6, 7, 8 points in the middle. Then if I add B at the end, that's 9, and A at the front, that's actually 10. So if I have 9 subintervals, I actually had 10 different points that I'm looking at. I'm going to construct the height of each rectangle at each subinterval using some value, I'll call it C, in the subinterval. In the last lesson, we looked at the left endpoint, the right endpoint, and the midpoint of the interval as places to choose. But I'm going to argue I can pick any one I want, and it will give me an estimate. We saw that in some situations one might be better than another. So I'm going to choose this value here. I'm going to take it up, and I'm going to draw my rectangle at that value. I'll do the same maybe from over here. Okay, kind of close to the right. Maybe I'll pick this one right here. And from going on from here, I'm not even going to draw it. I'm just going to take it up there and draw a rectangle. So I'm not choosing a, maybe this one will be a right endpoint. I'm not choosing one specific value to make my intervals at, right? Okay. Now I have this. You might find this unsettling though, because like I've got some rectangles and they're all different. They're all different widths, and the heights are constructed based on all sorts of different places. But it is an estimate for the area in the curve. All right. I'm going to let x equal c sub k be some point in the kth interval. So this is interval 1, 2, 3. I'm going to call this interval k just so we have a picture of it. So this is k, all right? And my height was drawn at some value x equals c, and each one of these intervals has a selected value c. So c sub 1 would be the c of the first interval. C sub 2 would be the c, that magical c I chose, of the second interval. So c sub k would be the interval of the kth interval. Okay. Can we find the area of rectangle k? Well, in terms of f of x, the area of rectangle k is the height times the base. The height is the function's value at that special c sub k. And the base is simply what? How would I find the base there? Well, I'm going to call that the change in x of the kth interval. So capital D delta, meaning change in x. Okay? So now I want to find a sum of all in rectangles. So I'm going to go with sigma I'm going to let k, my kth rectangle, start at rectangle 1 and go to rectangle n. And then I'll do f of my magical c for each one of these kth intervals times the width of each interval, which is the change in x from the left to the right. Okay. This sum is called a Riemann sum. So how we just to draw that symbol, I like to do a little flare on mine. You go, but basically you start on the upper hand corner. You do a horizontal line, then you go diagonal down, diagonal back, and then across. Now, here's my question for you. How can, and if you, I need you to take your paper. Actually, I need you to cover up the next statement. So do not look at that. Put a calculator, put your phone over it, put your hand over it. All right, but I want you to answer this question with your own knowledge. How can we ensure that this sum is equal to the exact area under the curve? This is what Riemann realizes. We can actually find the exact area under this curve. And you could think of it in calculus terms, or you can just think of it in just everyday language. What would we need? So let's take a look at this picture here that I've drawn. Why is this not a perfect area under this curve? Well, I've got some gap over here, don't I? Where this rectangle wasn't tall enough. But I have a question. Could I make this better if I were to take this big rectangle and make it smaller, right? And maybe then recalculate my C's using some strategy. I will get a better estimate most likely, wouldn't I? Can I do that again here? Can I split that in half? And then recalculate on each side of there? And then maybe split that in half? And that in half? And that in half? If I made my rectangles really thin and filled this region up with rectangles, each one absolutely razor thin, no matter what C value I choose to get the height. Since the margin between the left and right endpoint of each interval is so microscopically small, I would argue that there's going to be almost nothing wrong with that rectangle. So that's one way we could answer this. How could we do this? We could make each rectangle really, really thin. How thin? How thin? What's the word? Infinitely thin. Infinitely thin. Ooh, but I just thought of a question though. Okay, so but here's the issue. If these are infinitely thin, how many of them am I gonna need? I'm gonna need an infinite amount of them. It's going to take me an infinite amount of rectangles to go from A to B if they're infinitely thin. And I would argue that each statement implies the other. So you might think, now let's think like a calculus student, and we're ready to unveil this. What thing have we learned this year that we can use to evaluate things as they go towards infinity? A limit. We spent half the year studying derivatives, but a derivative is simply a limit, right? So we can use a limit. So, behold, the definite integral is the integral from a to b of f of x dx is equal to the limit as in the number of subintervals, or rectangles, if you will, goes to infinity, of our sum from k equals 1 to n of f of c sub k times delta x sub k. If we suppose that each subinterval is uniform in width, and we can make that assumption without changing the calculus much, we can clean this formula up a little bit. So if each subinterval is infinitely thin, but we call it uniform, then I don't need the delta x sub k. I can just call it delta x. And I can actually calculate what that delta x would have to be. It's a over b divided by n. If I have 10 subintervals and the difference from a to b is 10, I need each interval to be a width of 1, right? And the following definition gives us an equivalent definition. So I'm calling this the alternate. We can't be calculus without an alternate, right? This is the alternate definition of the definite integral. The integral from a to b of f of x dx is equal to the limit as delta x goes to 0 of the sum from k equals 1 to n of f of c sub k times delta x. Now, you have to know that we're assuming that a minus b over n is equal to delta x. So what is n? N is the number of subintervals, right? Now, here's the deal. If I'm sending this to 0, then this must be going to infinity. So these are equivalent definitions. I can either send the number of rectangles to infinity or send the width of each to 0, as we discussed earlier. If I'm going to be infinitely thin, I have to have an infinite number of them. Okay? All right. You have to memorize this definition. Let's talk just a little bit about calculus notation style. We've seen this before. Greek capital letters mean real numbers. So delta x is a real value, a real change in x. If I send delta x to 0, it becomes an infinitesimal. And in Calculus 1, for some reason, we still write this as a Phoenician d instead of the Greek lowercase delta, which looks more like that, but you'll actually switch. Eventually, you'll start seeing that more often. And then the capital sigma becomes the little curly s sigma. Why did they choose s for sigma? I think because of sum. S for sum. Okay? So it's a summing of an infinite number of infinitely thin rectangles, and we know that that can happen. That can be anything, right? All right. When a function is above the x-axis, the definite integral is equal to the area between the function's curve and the x-axis. That's what it is. The definite integral, when the curve is above the x-axis, is simply the area enclosed by that curve. But when the curve is below the x-axis, the area is a negative value. And that's because, remember our definition, it's got f of x in it. And if f of x is a negative number, this will be a negative value. So to say that the definite integral gives you the area under a curve is not 100% accurate. It can be used to find the area in the curve, but it is not the area under the curve. I call it a signed area under the curve. Let's take a look at some properties of the definite integral. This is important to have. If I take the definite integral from a to b, from a to a. So that'd be finding the area under the curve, the signed area under the curve of f from x equals 4 to x equals 4. I'd be having a width of 0. So I think we can agree that that must be 0. Next, we talked about that the integral from a to b of f of x, if f is above the x-axis, is a positive, but if f is below, it's negative. But if I do the integral from backwards and I switch these bounds, then I'm going to get a negative answer as well. Because now, instead of going from, say, x equals 1 to x equals 2, yes, it's an infinitely small number, but infinitesimals can be negative. So it makes more sense to think about it in terms of, delta x. So we've been looking at delta x going if this was 1 and this was 2, that'd be a delta x of 1. But if I'm going backwards, it'd be a delta x of negative 1. So if you switch these bounds, it gives you the negative of the other answer. And sometimes you want to go backwards. It just depends on the problem situation. For example, you might know how much water's in the tank right now and know the rate and want to figure out how much water there was 4 hours ago. All right, the integral from a to b of some constant k times f of x dx, I can pull constants out. Also, I can split this up. I can split up addition like so. Okay. And I can split up subtraction. So if I have these, I can make this into two smaller problems and subtract their results. Couple of things to note. One, there is no splitting up of multiplication. That's a not equal. This does not work at all. Just like when we were looking at derivatives, you can't do that. And you can't do that either. We can do it with limits, but we can't do it with integrals. One more thing I'd like to say is that there is no way to get the area under this curve by multiplying or adding just these heights. It does not make sense for me to estimate. In the previous lesson, we looked at estimating area under the curve. We had to do that. We had to take the height times the width, right? And despite the fact that we're saying that width can become infinitely thin, it would make no sense for me to talk about the integral from a to b of f of x without a dx. That'd be like finding the area of a rectangle that's actually not a rectangle but a segment. These might be infinitely thin rectangles, but they are always rectangles, and I must have that dx there. All right. Let's try and evaluate the integral from 1 to 6 of 4 dx. Ready? Okay. This is actually asking us to find the area under the curve when f of x is equal to 4. So I'm just going to find y equals 4 and draw that line. And we're going from x equals 1 to x equals 6. So we can find this definite integral very easily by simply multiplying 5 times 4 equals 20. And I'm going to discuss how to check this with our calculator. And we will need, it is absolutely required for all AP calculus students to be able to do a numeric integral, to numerically approximate a definite integral. Every calculator can do it. Even non-graphing calculators, as long as they're scientific, have the function. That's just usually very cumbersome to type in. So we use second 8 a lot when doing the derivative. You'll look to the left, you see second 7. It's also under the F3 calculus menu. So second 7, integrate. We're going to put a 4. First you put the expression. Then you put a comma, and you have to tell it whether it's dx or not. Turns out, later on we'll see, we could do our rectangles, instead of going up and down, we could do them horizontal and be dy. So we got to tell it we're doing dx. And then you tell it the bounds on x are from 1 to 6. So you put 1 comma 6, close the parenthesis, and make sure you check the pretty print. It should make it look like the integral you're doing, and we get 20, which is exactly what we got. All right. Next we'll do the integral from 1 to 3 of x plus 2. X plus 2 has an intercept at 2, right? When x equals 1, it's at 3. I think it's just got a flip of 1 here. When x equals 2, I think we're at 4. And when x equals 3, 5. So it makes this shape right here. But I want to find the integral from 1 to 3. So it's going to be this region here. And that's a trapezoid. I can figure that out. Area equals 1/2 the first base, which is a height of, looks like 3. And the second base is a height of 5. Times my height going across here, which is just 2. So that's 1/2 times 8 times 2, which is 8. All right. Here's a shape. The square root of 4 minus x squared. This is a shape that every calculus student needs to know because they'll ask you this and you to make sure that you know how to use a geometric formula. So you need to know how to do this. We're going to learn lots of tips and tricks to try and make these things easier, but I'm never going to make this one easier. Well, not in AB class. And even then. So from negative 2 to 2, this is a semicircle. X squared plus y squared equals 4 is a circle with radius 4. If you solve that for y, you get 4 minus x squared. Take the square root of it. So it's the top half with a radius of 2. Okay? So this must be equal to 1/2 the area of this circle because we're only looking at the top half. So it's 1/2 pi r is 2 squared. So 2 pi. 2 pi is that definite integral. All right, let's try this next one. The integral from negative 4 to 4 of f of x dx. So negative 1, 2, 3, 4. So in this area over here, I'm going from negative 4 to 1, 2, 3, 4. This area here, though, is going to be negative because it's below the x-axis. So let's find that area. That's a triangle. 1/2 base times height, so that's 2 times 3. But it's going to be a negative. All right, next, we got this region up here, which I'll use blue to show it's going to be positive. And it's 1/2 base times height again. So 1/2, the base here is 1, 2, 3, and the height is 1, 2, 3. Okay. And then we have another one down here, which is again negative. So plus negative 1/2, 2 times 1. So that would be negative 3 plus 9 over 2 minus 1. So negative 6 over 2 plus 9 over 2 minus 2 over 2 is 1 over 2. Okay. All right, let's do a few more. We're going to take the integral. We're given some information about an integral. We're given that the integral from 0 to 3 of f of x dx is equal to 4. And we're given that the integral from 3 to 7 of f of x dx is equal to negative 1. So our first question is, what's the integral from 0 to 7 of f of x dx? Can I simply add these two together? Well, it turns out I can because of the properties that we discussed on the previous page here. So I would normally just say the answer, but for our notes, let's show how this works. We can split this integral up like this. Actually, I'm looking at the wrong justification on that one. What allows me to say this? Well, I don't think I gave it to us on here, but it's most assuredly true. Most assuredly true. So I guess I could have called it one more property, but I kind of feel like too many properties at once gets a little awful. So, but yeah, I think your intuition serves you well here. So 4, and then that's a negative 1, so the answer must be 3. Now, we definitely did give you this property. We can actually pull that constant out in front, like so. And so now I know the integral from 3 to 7 is negative 1, so that's 2 times the negative 1, so that's a negative 2. The integral from 5 to 5 of f of x dx, I don't know what f of x is, but I know that's 0. The integral from 5 to itself is 0. Now, the integral from 3 to 0 of f of x dx, that's backwards. That's a backwards integral because usually the small number's on bottom and the big number's on top because it's telling us to start here and go to there. So that's equal to negative the integral from 0 to 3 of f of x dx. So it's actually just negative of our answer, so it's negative 4. All right, I have one practice problem for you to do, but it's got, of course, like 800 parts, even subparts. The graph below represents f prime of x. So this is f prime of x, okay? I want you to find the values of x where f has a relative extrema and tell me what kind they are. Then I want you to evaluate each one of these statements and then tell me on what intervals f is increasing and on what intervals f is concave up. Give it a try now, please. All right, so let's go over what we got. At what value does f have a relative extrema? Well, we can see that we have a relative extrema at x equals 2. Because f prime of 2 equals 0. Now, f prime of negative 3 also equals 0, but it's making it a critical number, but it's not an extrema because it didn't change from positive to negative. X equals 2 actually locates a relative maximum, though, because f prime changed from positive to negative. Can we see that? That must have been a relative maximum of f because the derivative changed from above to below. We can also do some integrals with derivatives. So let's do the integral from negative 5 to 3. Well, that'd be the area under the curve, the signed area, from negative 5 to 3. So that's 1/2 a triangle, right? Base of 2, height of 2, so just 2. Now the integral from negative 5 to 2, I need to positive 2, sorry. So I'll need to take this triangle and add in this other triangle. So that's a base of 1, 2, 3, 4, 5 times 1, 2, 3. So 15 over 2. So it'll be 2 plus 15 over 2, which is 19 over 2. And then we got negative 5 to 4. Well, I got to take that triangle, and then subtract that triangle. So our first two triangles were 19 over 2. Now we're going to subtract 1/2 times 2 times 3. So that's 19 over 2 minus 3, which is, I think, 13 over 2. On what intervals is f increasing? Well, f is increasing on the interval from negative 5 to 2 because f prime of x is greater than 0. On what interval is it concave up? Concave up means the derivative is increasing. So that would be on the interval from negative 3 to 0. Because f prime is increasing. So as you can see, we've added more tools to our toolkit. We can now start talking not just about the shape of f, but we can start talking about areas involved with f. And we'll see a greater connection grow over the course of this unit. So that's it.